This is the algorithm what we saw in the previous class. We also have implemented in Colab and saw how a linear boundary can be identified, can be learned, or the weight parameters that define the line W0, W1, W2 can be learned by the perceptron by iteratively inputting the input samples one after another, computing the output by the perceptron, and then propagating the error, if any, after projecting it onto the input sample so that the weights are modified. So this is the key equation which modifies the weights, where this error of classification is projected onto the input vector and then used in modifying the weight. This is the individual weight version, and this is the vectorization version, where all the weights are updated at a time. And the error is projected onto the input sample vector, x bar. So this can be thought of as x bar, and this error t minus o vector is projected onto this. The dot product is calculated, and as a result, the classification boundary changes its orientation gradually and finally reaches the correct orientation. Now we would like to go ahead. We said that in the previous class, in fact, one of the participants asked, what are the limitations of perceptron? In fact, the limitation of a perceptron is that it can only identify a linear decision boundary when the training samples are linearly separable. So they should be linearly separable in a sense that there should exist a linear boundary such that one class of samples fall on one side of the boundary and another class of samples fall on the other side of the boundary. So it should exist basically. So if it exists, it will be able to identify. If it does not exist, then perceptron will not be able to identify the correct boundary of classification. The best example is here. Now in this case, there exists a boundary of this kind. We may know it, we may not know it, but it exists. And the perceptron learning algorithm, after inputting these training samples, will be able to identify this. Whereas here, if you look at the 4 samples shown in the Cartesian plan, this is one Cartesian plane, one sample, this is the second sample, this is the third, this is the fourth sample. Out of these 4 samples, you have 2 positive samples and 2 negative samples. So how much ever you try, you realize that there is no linear boundary that exists by virtue of the nature of input samples. The input samples are like that. So we cannot blame anybody. They are not linearly separable. Suppose if I draw a line like this, on this side I have 1 positive sample and on this side I have 2 negative samples and 1 positive. Suppose I draw a line like this. On this side I have 1 negative sample and on this side I have 2 positive and 1 negative sample. If I draw a line like this, I have 1 positive and 1 negative sample on either side. So whatever you do, you will not be able to find out a decision boundary here. Probably the decision boundary should be like this. So I'll draw it separately so that the decision boundary should be like this. so that the positive sample is, all the positive samples are here. And the negative samples are here. Or instead of this, it could be this way also. You can identify a decision boundary of this kind also. So that's not possible with Perceptron. Then what is the solution? What is the alternative? The alternative is a neural network in simple terms. And the fundamental unit of neural network is a sigmoid unit. In fact, one sigmoid unit, if you take, it once again will be able to classify only samples which are linearly separable. So a perceptron and a sigmoid unit are one and the same. But however, we emphasize on sigmoid unit because if you move on to a network of sigmoid units, then probably you get the power of being able to identifying non-linear decision boundaries. So that's the reason why we look at sigmoid unit. One may argue that a sigmoid unit by itself is also capable of identifying only linear decision boundaries. Yes, agreed. But it has a better way of identifying the linear decision boundary. It presents itself in a better way than the perceptron. And when multiple sigmoid units are combined and organized as layers, which results in multi-layer perceptron, MLP, which is equivalent to neural network. I told you there is a jargon of terminology in machine learning. So MLP and neural network, they're one and the same. So that's the reason why today in this class we start with sigmoid unit. So by this time you might have got the hang of a machine learning model. You have seen perceptron. So perceptron has an intrinsic structure. It has some model parameters, and then it has a principle of working. And these parameters are learned by the learning algorithm associated with the perceptron. So this is the framework of any machine learning model. You have a model, principle of working of the model or model behavior, and then you have inputs to the model, you have outputs from the model. There are some hyperparameters of the model. Hyperparameters are fixed parameters. Hyperparameters of the model, and some parameters learned based on the given input. Good. There was some kind of disturbance from one of the users' mic. So we were talking about sigmoid unit. So I was trying to elucidate the generic behavior of any machine learning model after looking at the perceptron. So you have a model. Model has some hyperparameters and trainable parameters, learnable parameters, and then a principle of working, input and output. So the principle of working of the model is fixed. The researchers have identified the different models and their principle of working. Their hyperparameters are fixed. The inputs and outputs are fixed. The only thing is the model should learn the parameters or those parameters which are to be learnable. So those parameters are to be learned by using the model algorithm, by inputting the training samples. And once the model becomes ready, It can test the test samples and it can forecast the output for a new unseen sample, either in the test set or that comes in a future time. So sigmoid unit is also a binary classifier, as I said. Now the class labels are given as 0 and 1, not 1 and -1. The class labels are given 0 and 1. And what is the working principle of sigmoid unit? The working principle of sigmoid unit is almost similar to the perceptron. It calculates the network sum when it classifies. When it is ready for classification, it is understood that the weights are already learnt, the parameters are already learnt. So when you give an input sample, it will calculate the network sum. And yesterday we have seen the network sum is sigma j is equal to 0 to d wj xj I. Means network sum for the ith sample. Network sum for the ith sample. So if you know which sample are you talking of, then you can conveniently avoid I as well. But in some of the derivations, you need this I when you are talking about all the input samples. So when you know the sample at hand, you can as well avoid it and say the network sum is sigma j is equal to 0 to d, because there are d plus 1 input parameters, features. D features come from the sample and we add one bias. So D plus 1 features, WJXJ. And then the sigmoid unit differs the way it applies the activation function. It applies the activation function. So this here we introduce another term, activation function. So the activation function is a sigmoid function. That's why it's called a sigmoid function. And the sigmoid function, the sigmoid functions are a family of functions. And the sigmoid function, what we use here is designated as sigma x is equal to 1 by 1 plus e power minus x. This is the sigmoid function. So now we have calculated the network sum. So we apply the sigmoid function. So sigma net. In place of x, we substitute net so that you get the output of the activation. So this x will be replaced by net and you will calculate 1 by 1 plus e power minus net, where net is the network sum of a particular sample. And by the very nature of the sigmoid function, the output will lie between 0 and 1, as shown in this diagram. So from -6 to 6, the value ranges from 0 to 1. The output value ranges from 0 to 1. So that should raise a question. We are talking about a binary classifier. So the output should be, when I input the sample, x0, x1, xd, and calculate the network sum, sigma j is equal to 0 to d wj xj, and apply the sigmoid function on it, I should get either 0 or 1, which happened in the case of a perceptron, where thresholding results in either -1 or +1. And here we said that the class labels are 0 and 1. We'll encode the class labels as 0 and 1. When we say class labels are 0 and 1, what we mean is we take the real world data and replace the real world terminology of classes by encoding them as 0 and 1. For example, you have a lot of data related to mails. Some of the mails are spam and some of the mails are ham. So when you prepare the data set, the word spam is replaced by 0 and the word ham is replaced by 1. So that way encoding is to be done by 0 and 1. So that's fine. So we expect the sigmoid unit to output 0 and 1. But the very nature of the sigmoid function says that it outputs a value between 0 and 1. So how is this behavior compatible with our expectation? In fact, this kind of behavior is not a drawback. This kind of behavior of sigmoid unit enables the sigmoid unit to extend its applicability to nonlinear classification problem domains as well. How does it happen? It's simple. You look at the values resulting after the sigmoid activation, not as absolute values of class 0 and 1. Instead, you look at them as the probability of the sample belonging to class 1, and hence 0 will say that the probability of belonging to class 1 is 0 and hence it is class 0, and 1 value says that the probability of input sample belonging to class 1 is 1 and hence 1 represents the class 1. So it's a very nice idea. I repeat once again. So the output 0 or 1, which we are expecting, instead of looking at that as the class label, please slightly modify your perception. Suppose this 0 says the probability of I have input here, and this is my sigmoid unit. This is the output 0 and 1. So don't look at this 0 and 1 as the class label. Look at 0 as probability of the input sample I bar, yes, input sample belonging to class 1. Belonging to class 1. So what is the value here? 0. That is the probability of input sample belonging to class 1 is 0. Then how do you judge your input sample as? Your input sample belongs to class 0. Because the probability of it being belonging to class 1 is 0, it should belong to class 0. So that's how I look at it. And let's see here. This is the probability of input sample belonging to class 1. If I look at this one as the probability of input sample belonging to class 1, what does it mean? The input sample belongs to class 1. So absolutely fine. So the output of the sigmoid unit, if you look at the output, instead of the class label as the probability of input sample belonging to class 1, then sigmoid unit should work perfectly. Because if you get a value of 0.9, because sigmoid unit gives the values between 0 and 1. Suppose you get 0.9 as output, then probability of input sample belonging to class 1 is 0.9. So how should it be inferred as? It should be inferred as that the input sample belongs to class 1. The output value is 0.6. So it is justified because the probability is greater than 0.5. The input sample is likely to belong to class 1. Suppose the probability, the value output by the sigmoid unit for a particular sample is 0.4. Because it is less than 0.5, I'll say that the probability of it belonging to class 1 is 0.4 only. It is much less than 0.5, and hence I'll regard the input sample as belonging to class 0. So you see that this is a major change in the perception of the output value, and this helps a lot in visualizing the outputs as representatives of class labels. So they are not exactly class labels. The output is not exactly class labels, but the output gives us some kind of hint regarding what class of sample is input currently to the model by emitting out probability values. Any questions? Okay. And the sigmoid function has a very beautiful property. Uh, this is what I have expressed so far. It got slightly shifted. So you realize that all the explanation what I made so far can be felt in this slide. Sigmoid unit. It's not perceptron. It's mistitled as perceptron. It is a sigmoid unit because it is not a step function here. What I have shown. What I have shown here is a sigmoid function. This is a sigmoid function. And now there is an important property of sigmoid function, which is very much useful in designing the learning algorithm for sigmoid unit. Once again, we need to talk about the learning algorithm for sigmoid unit. The principle of working is different. So quite obviously, the learning algorithm, what we have adopted in the case of a perceptron cannot be adopted here. And that's what I have been instructing all the novices in machine learning, that please remember every model will have its associated learning algorithm. So you have to design a new learning algorithm for the sigmoid unit. So the researchers have given us a nice algorithm, learning algorithm for sigmoid unit. So as a precursor to the algorithm, I would like to state one property of the sigmoid function because this property is used in designing the learning algorithm. Let's look at the derivative of the sigmoid function. Why we need the derivative will be explained shortly. So the derivative of the sigmoid function is d sigma x by dx is derivative of 1 by 1 plus e power minus x. So the derivative of 1 by x is minus 1 by x square. We know that. So derivative of sigma x is minus 1 by f of x whole square because f of x is 1 plus e power minus x. We have to use the chain rule of derivation. So minus 1 by 1 plus e power minus x whole square multiplied by the derivative of 1 plus e power minus x. The derivative of 1 plus e power minus x, the derivative of 1 is 0, 0 plus the derivative of e power minus x. The derivative of e power x is e power x. So the derivative of e power x is e power minus x is e power minus x. And then what we had is a composite function. It's not e power x, it is e power minus x. So we, by chain rule, we take a derivative of minus x, which is minus 1. So ultimately, we see that the derivative is e power minus x by 1 plus e power minus x whole square. And keep at the back of your mind that this is not just merely x. In our application, this is going to be our network sum because the sigmoid activation function is applied to the network sum. So please keep at the back of your mind, keep at the back of your mind that this x is not just a variable, but in our application it is going to be our network sum. Can anybody tell me what is the network sum? That's a very simple basic question. No? Just now I told you, yeah, please. User 219, you have switched on your video. Okay, the network sum is nothing but the sum of the products of weights and the corresponding input feature values. Weights and feature values. There was a question from user 27. In sigmoid function, shall we consider 0.5 is default threshold value or fixed value? Can you make the question more clear? Yeah, Daniel has answered the question. Some of the products of input and weights. Participant 27. Can you make your question more clear? Sigmoid function, shall we consider 0.5? Okay. So that's e power minus x by 1 plus e power minus x whole square. Let's see what more can be done to this. So we can express this as a product because we have a square in the denominator. So I'll express it as 1 plus e power minus x into 1 plus e power minus x as a product of these inverse functions 1 by 1 plus e power minus x, and we move e power minus x to one of the terms. Good. This e power minus x by 1 plus e power minus x can be written as 1 minus 1 by 1 plus e power minus x. By taking an LCM, you can cross check. 1 plus e power minus x minus 1. So it will become e power minus x divided by 1 plus e power minus x. But we know that sigma x is 1 by 1 plus e power minus x. So you can substitute sigma x, because sigma x is 1 by 1 plus e power minus x whose derivative is being calculated by us. And this is sigma x. So ultimately it becomes sigma x into 1 minus sigma x, which is a very elegant property of the sigmoid function. And what is sigma x? Can you anybody tell me the physical significance of sigma x when you apply it to the model? Yeah, I will watch the chat box also because some of you are typing in the. Sigma x is nothing but the output of our model. Because x is a network sum, we apply the sigmoid function, then what you get is the outputs. So this is nothing but O, this is nothing but O. So O into minus O. O is the output from the model. Because in the previous slide, I said O of x naught, x1, x2, xd is nothing but 1 by 1 plus e power net. So that's how this is a very elegant property of the sigmoid unit. Yeah, there was a question. Does the threshold of 0.5 remain constant? Should we take greater than 0.5 as class 1 and less than 0.5 as class 0? Always. Not necessarily. As a machine learning application engineer, you know about your data set. So how credible your data set is, how correct your data set is, how well features represent the domain characteristics. So it depends on several factors. But the thumb rule which we follow in our human life is anything greater than 0.5 belongs to probability of 0.5 is likely to belong to one category, and a probability value less than 0.5 talks of another possibility or another category or another class. So that's how we all humans are accustomed to think and use probability in real world judgment. Because ultimately there should be one benchmark. So the benchmark is 0.5. In fact, in our real life also, we say there is a 50-50 chance when you want to give equal possibility for both the chances. But you will never say 60-40 to say that equal possibility is there for both possibilities. That's how you are trained. We are used to. So that's the reason why naturally 0.5 is a decisive benchmark in normal circumstances. But otherwise, if you feel that, uh, suppose I'll give you a real world example where 0.5 does not work. 0.5 does not work. Suppose you have a data set in which you have data related to bank fraudsters is there. So there are two kinds of possible data of bank customers: fraud or fraudulent and non-fraudulent, 0 and 1. Now, can anybody tell me what could be the percentage of fraudulent customers and what could be the percentage of non-fraudulent customers? User 27 and Daniel Rauri, you have focused on this question. So I have given you a simple question for thinking. You have bank customer data in which you have fraudulent customers and non-fraudulent customers. Now, can you tell me what is likely to be the percentage of fraudulent customers? What is the percentage of non-fraudulent customers? Because it's a good question. Whether shall we take 0.5 as the hard-coded threshold value to decide upon whether the input sample belongs to class 1 or class 0? Yes, my dears?
Sir, that depends on the percentage of the fraud and non-fraud customers, no, sir.
Exactly. Now you got the answer to your question. Does the threshold change or does the threshold fix?
For example, fraud may be 25% and non-fraud may be 75%. Then how can we choose the threshold value using this model?
That's what I'm telling you. In fact, to realize the answer by yourself, I have raised the question and shifted your focus to thinking about the real world domain. Now, while answering this question, you might have realized that because the input does not compose of 50% fraudulent and 50% non-fraudulent, so automatically the answer might have struck to your mind that yes, it cannot be 0.5. It depends on my data set as well. Am I right, Mr. Daniel?
Yes, sir.
Yeah, that's the reason why I asked that question. Because if your data consists of mostly fraudulent and fraudulent is encoded as 1, fraudulent is encoded as 1, then maybe instead of 0.5 you will take 0.3 or 0.4, 0.2 because there is every possibility. If it is not 0, there is every possibility that he is a fraudulent customer. So that way, in that case, you would like to tighten your threshold value of identifying the input customer as fraudulent to limit it to 0.2 or 0.3. You don't want to accommodate any kind of probability of being fraudulent and fraudulent being encoded as 1. Suppose it is the other way around. There are 90% of non-fraudulent customers and 10% of fraudulent customers. I think you should realize the answer on your own now, Daniel. What will you do if there are 90% of non-fraudulent customers and 10% of fraudulent customers?
I think the most of the percentage is positive side, and there is may not be to classify them. Is that correct, sir?
See, when we are trying to answer this question, we would like to make the audience understand. So we take the extreme examples so that you will immediately understand the meaning of 10 and 90. But it doesn't mean that our data sample consists of 10 and 90 and we are still classifying what is the need of classification. No. The idea here is when I take 10 and 90, I am trying to enlighten you to get the answer and to understand the answer quickly. So 10 and 90 cannot be taken as it is. It could be 30 and 70. It could be 40 and 60. It could be 35 and 65. What will you do? I said 10 so that you can quickly understand. But it does not be projected onto whether we should classify or not classify. That is not the essence here.
Okay.
Essence is to make you understand. Normally, when you take one's cognition to extreme values, they'll quickly understand. So that's the reason I took your attention to an extreme value so that you can easily understand that when there are more non-fraudulent customers, then even 0.2, 0.3 also is good enough, unless it is 0. If it comes to straightforward 0 and fraudulent is encoded as 0, then you have to accept it. But 0.2, 0.3, 0.4 is the probability of being a non-fraudulent customer, because non-fraudulent is encoded as 1. And then you say that, okay, he likely to be non-fraudulent because most of the customers are non-fraudulent, and 0.3 is good enough in these circumstances. So that way, maybe as matured participants, you cannot hard code decisions and you cannot hard code some kind of formula where you substitute on the left hand side and on the right hand side you get an answer. It cannot be, because basically machine learning is predictive learning. You believe that all the samples what we have belong to a probability distribution. That is the foundation of machine learning. They manifest a probability distribution. They belong. They are not random. They are not sporadic. They are very regular. They belong to a probability distribution. So predictive learning is built on these foundations. So, and we expect that in future also the same probability distribution continues. And it is the nature of the probability distribution, parameters of the probability distribution affect the decisions to some extent and do not allow us to hard code our interpretations. Is this clear? No, it's
Yes,
not a
sir.
it's not a smart answer, Daniel. It is a correct answer. There is a difference between smart answer and correct answer. So it's not smart. It is correct
As a,
answer.
yes, sir. Yes.
So the principle of the learning algorithm. Now let's look at the learning algorithm of the sigmoid unit. The learning algorithm of the sigmoid unit has a different principle. If you look at the perceptron, you might have wondered, I'm not sure, but nobody has expressed any question on that. I have given you the learning rule. I haven't given you the foundation of the learning rule. Nobody asked me, sir, how do you prove that this is a correct learning law? How is it justified? Nobody has asked me, but it's good. Nobody has asked me because it was an empirical, geometrically proved learning rule where Wj equal to Wj plus alpha into T minus O into Xj, where Xj represents the feature value, T represents the target label, O represents the output label from the model. But in sigmoid unit, I have the obligation of telling you the principle of the learning algorithm and how is the learning algorithm designed, what are the foundations for designing the learning algorithm itself. And in fact, I'll tell you, this is one more key aspect of machine learning algorithms because the same philosophy, the same principle is manifested again and again. That's what I would like to tell all the participants. If you learn the key aspects of machine learning, navigating from simple to complex models becomes easier for you because it's a continuous learning. So don't think that you have to start from zero every time. No, your previous perceptions will be useful to you most of the time. But you should be able to identify what are those patterns of learning that will repeat again and again and be good at that pattern of learning. I'm telling you this from a pedagogical perspective. So the principle of learning algorithm, if you try to understand the principle of any learning algorithm, then it would be very simple to implement that model. And you will be able to understand that model. If you want to even tweak that model, if you want to modify that model slightly and apply to your data as a research extension, it will be simple. And if you do not go to the internal principle and if you work on the periphery, then probably you have to only use that again and again. You will not be able to bring any applicability by tweaking to some specific domains or some peculiar domains. So here the principle of the learning algorithm is to define an error function prediction and find the weights to minimize the error of the prediction. So we know that for every input sample and for a given set of parameters of the model or weights of the model predicts the label as 1 or 0. So you give an input sample, you get an output. You give an input sample, you get an output, assuming that the weights are fixed. Now you define an error function. What is the output given by my model and what is the output I have to get from my model? T is the target label, O is the output label. So you define an error function in terms of T and O. If you define an error function, then you will have a mathematical foundation which will help you to design the algorithm where the algorithm absorbs the minimization of the error. The algorithm will absorb the minimization of the error. And what should be the values of the parameters to minimize the error, because error is defined by a function. So the clue is define an error function and try to find out what should be the parameters so that the error function is minimized. So your learning algorithm should be designed. Once a learning algorithm has been designed, you use the learning algorithm. That's a different thing because you have the learning algorithm at your hand. But I am focusing on how people design learning algorithms, how that learning algorithm might have originated. So the learning algorithm normally originates by following the philosophy of defining an error function and seeing how the parameters are to be modified so that the error function is minimized. And this concept is expressed in the form of computational steps, and all the computational steps put together will become automatically the learning algorithm. Now the error function defined in case of sigmoid unit, and in fact in most cases of models which use gradient descent algorithm, is E of W. The error function is dependent on the weight vector because inputs cannot be changed, outputs are given. So the only variable parameters in our model is weights. So that's the independent parameter. So E of W is 1 by 2n because there are n samples. Sigma I is equal to 1 to n for each sample. Ti minus Oi. What is the target label? And what should be the output label given by our model? Whole square. So this seems to be a reasonable and quite rational and justified error function, because it is trying to find out the average of the square of the error. Average of the square of the error. That's why it's called as mean square error. Mean square error. So this is the error. This is the error. It is squared here and it is meaned here. So it's not a grammatically valid usage, but mean square error. You can see all the three aspects here. Mean, square, and error. So now suppose your model has weights in such a way that if it becomes 0, what does it mean by 0? You have calculated for the first sample what is the output label and what is the target label. They are one and the same. So this is 0. 0 square is 0. For the second sample, for existing weights, you calculated the output and you got the output and the target as same, so 0. So you see that the whole sum is equal to 0, which means that the error is 0. And if the error is 0, my weights are supposed to be correct because all the input samples are classified correctly. Now, we would like to find out a rule which will help us in minimizing the error. This slide and the graphic on this slide should explain you the error function what we have seen just now. For the case of a single weight, of course, here I have given you a vector. There will be more than one weights. But without losing the generality, let's look at the relationship between weight and the error function. Excuse me. In case of one weight. So we know that there is a convex function. The error is like a parabola because it is sigma is equal to 1 to n ti minus oi whole square. So this is the error function. And we knew in the case of perceptron or in the case of any model of machine learning, normally we assume some weight and start. We assume some weight and then go ahead to modify so that you will improvise. So what is that modification rule? That modification rule now should be given by our error function because we have defined our error function. We have a well-defined equation for our error function. So by the behavior of the error function, by the nature of the error function, we should be able to know what should we do to our W so that the error will be reduced. And in case of mean square error, the rule that gives you, the algorithm that gives you to minimize the error is called as the gradient descent rule or gradient descent method or gradient descent algorithm. When you look at only the rule, you call it as gradient descent rule. When you look at the whole of the algorithm which uses this rule, you call it as gradient descent algorithm. Actually, somehow I believe that it is misnomered as gradient descent algorithm. Actually, it is gradient descent rule which is used in the process and as a result of which the algorithm is also called as gradient descent algorithm. What does the gradient descent say? It's very interesting. Suppose this is my initial weight, W superscript 1. Superscript indicates different values of the weights of the same weight variable. For example, Let me call it as W3, Mudo weight, the third weight. And the initial value of the third weight is here. And this is the corresponding error. Now, how should I modify my weight so that I'll be able to get a zero error and I'll be able to reach this value of W3, which I'll call it as W3 final. This is W31. My intention is to move to W3 final. Because W31 gives this error, W3 final gives a zero error or minimum error. It's not zero error, the error is minimized here. If this curve touches the x-axis, then you will get ideally zero error. So I would like to minimize. So that W3 final. So it says this new W should be equal to old W minus alpha into gradient of the error function at, because the gradient is nothing but gradient in two-dimensional is slope. Slope in multi-dimensional is called as gradient. So you can also call it as slope for the time being in this example. So it says the old weight minus alpha into slope of the curve, but the curve is widespread. Which slope are we talking about? The slope at the current weight, the slope at the current value. The slope at the current value is obtained from this line. You draw a tangent here and you can easily calculate the slope. That is, you can easily calculate the value of dou EW by dou W, or in simple dou E by dou W. I say dou W partial differential term because W is a vector. W is not of single variable. If it is a single variable, we take derivative, but it is a multivariable function. So hence you have to take a partial derivative. So W minus alpha into the partial derivative of error function dou E by dou W. It's very interesting to know how does it work. It works because most of the people think that the magnitude will lead us to the minimization. Unfortunately, it's not so, because slope is defined as change in the y coordinate for unit change in the x coordinate. So the slope always talks about the change in the y coordinate for unit change in the x coordinate. So how is that value useful to be added or subtracted from the x value? So it is not the magnitude actually the authors have thought of in gradient in designing the gradient descent rule. Basically, the authors looked at the possibility or the reality that the slope of this line here is positive. So alpha into positive value results in a positive value, and W minus positive value will result in the reduction of W, and this W slowly moves towards this side. If you keep the value of alpha as small as possible, you get 0.01, something like that. Then you take the gradient or slope and multiply that and subtract from the original weight, you get the new weight. And at the new weight, definitely the new weight will move this way. Just now I have proved that the weight will move to the left because this is going to be absolutely a negative value only. Alpha is positive, the slope is positive. And hence the error will be decreased. So this would be the error. Yes, I am slowly moving towards the minimum error because this point corresponds to the minimum error. I'll do it one more time. I'll move here. I'll do it one more time. I'll move here. I'll do it one more time. I'll move here. And remember, this should be done as slowly as possible, because of which we multiply the gradient or slope value by a small value of alpha in the range of 0.01 or 0.1 and 0.2, and hence it is called as learning rate. This is called as learning rate. The rate at which it learns the correct value of W. It should not be hasty. It should not hasten up, and it should not quickly run towards finding out the correct value. You know what happens? If alpha is very large, from the explanation so far, you can easily realize that you may overshoot this minimum point and go this side. So you will end up here. So once again, error would be there. You have changed your weight, but error would be there. It is so unfortunate. So you should incrementally, in small amounts, try to change the value of weight so that you will never shoot up and miss that global minimum. I say global minimum because this is a very simple error function, but in reality, you may have an error function like this. So this is a minimum, this is a minimum, this is another minimum, and this is a global minimum. So you should never miss that global minimum. In fact, yesterday there was a question, sir, learning rate, is it fixed? And I said, please wait. In the next session, I will explain you what is learning rate. Probably this is the answer. Why learning rate should be small. If the learning rate is high, if your error is here, you will shoot here, then you will shoot here, then you will shoot here, then you will shoot here, and you will miss eternally the global minimum. But if you do it in incrementally small amounts and keep the value of alpha as low as possible, there is no possibility of missing this minimum value. You will definitely reach the minimum value. Okay, this is one side of the coin. The other side of the coin, somebody may say that, sir, you have very conveniently said that your initial weight W31 is here. What happens if W31 is here? Can anybody tell me what happens if my initial value, what I assumed, is here? Does the gradient descent rule still work? Yes, please. Are there any participants who are listening? Hello. Okay, whether you answer my question or not, at least you can type in chat box hi. Just type a hi. Okay, very good. Okay, if I assume the initial weight, rather knowingly or unknowingly, in fact, you never knew what is the correct weight. So most of the time we do it unknowingly only. So if it so happens that you have assumed the initial weight to be here, then you see that if you take the slope here, the slope here is negative. Your error function has a very nice characteristic that the slope of the curve to the right of the minimum point is positive and the slope to the left of the minimum point is negative. So it is negative and hence dou E by dou W is negative, alpha is positive, and this negative is being subtracted, which means it becomes a positive value and gets added. And if you get a positive value and get added, your W3 will move towards right, which is an indication that you are moving towards the global minimum. So that way you see that a gradient descent rule, it's a master rule for several machine learning algorithms. W equal to W minus alpha into the gradient. Now I have explained you for the sake of simplicity and without losing generality in case of a single weight. Now if you go for multiple weights, then the error function will be a hyperplane, and the update rule is change in W is minus alpha into gradient of the error function. This symbol is gradient. This inverted triangle is gradient. We say gradient because it's a vector. And this gradient is a vector of slopes dou EW by dou W naught, dou EW by dou WJ, dou EW by dou WD with respect to each weight. And then we get the final weight as original weight plus the change what you have calculated as minus alpha into gradient. If you express it for individual weights, it will be Wj plus delta Wj. And delta Wj is nothing but alpha into dou EW by dou Wj. You have to differentiate the error function with respect to that weight to get the value with which you have to modify the weight. A weight naite modify cheyalo, the weight which needs to be modified should get the delta value as alpha into differential, a partial differential of the error function with respect to the same weight. With respect to the same weight at that original weight. So that's the sigmoid rule, and the stochastic gradient descent rule says that Wj equal to Wj plus delta Wj, and delta Wj is alpha into differential of error function with respect to the same weight. The batch gradient descent says a different thing. What is the difference between stochastic gradient descent and batch gradient descent? In stochastic gradient descent, what we do is we update the weights after each and every sample has been input and the error has been identified. Whereas in batch gradient descent, you input all the input samples and then calculate the average gradient. Calculate the average gradient. You calculate gradient at each and every point, but you do not immediately project it onto the weight to change the weight. Instead, you sum up all the gradients, you take an average, and then you update your weights, which means that the weights are updated after each and every sample has been submitted by applying the gradient descent rule in case of stochastic gradient descent algorithm. Whereas all the samples are input, calculate the average gradient, and then use this average gradient to update the weights once for the whole batch, and hence it is called as batch gradient descent algorithm. So that's the difference between stochastic gradient descent and batch gradient descent. Now let's see the details of this principle. The error is defined as stochastic gradient descent is simple because you will be talking about only one input sample. So when you take one input sample, it has been input, you got a T, you have to get T and you got O, and the error is half into T minus O whole square. Now our interest is to calculate dou E by dou Wj or dou E by dou Wk because weight vector is there. So now this is half into T minus. In case of sigmoid unit, what is O? O is nothing but the output of the activation function to which the network sum is submitted. So sigma of net whole square. Now let's look at the differential with respect to partial differential with respect to one of the weights Wj. So dou E by dou Wj is half. This is a composite function. So we apply the chain rule. So half into 2, 2 and 2 get cancelled. To t minus sigma of net, t minus of sigma net. Derivative of t is 0. And derivative of sigma net, that is minus dou sigma of net by dou net, into, because once again it is a composite function, dou net by dou Wj. So this is the chain rule. Now if we expand this chain rule, t minus sigma of net into, if this 0 is ignored, it becomes minus 1. And the derivative of the sigmoid function, just now we have seen sigma x into 1 minus x. So sigma net into 1 minus sigma net. And derivative of the network sum with respect to Wj. What is network sum? We know that the network sum is W naught x naught plus W1 x1 blah 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 plus Wj xj plus blah 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 Wd xd. This is our network sum, where we have d plus 1 dimensional input feature vector. So when you differentiate with respect to Wj, you see that the differential of all these terms which do not contain Wj become constants and it is equal to 0. And this is the only term which consists of Wj. This is the product Wj into xj. So the partial differential of Wj xj with respect to Wj is nothing but xj. So that's how you. And this sigma of net is nothing but O, the value output. So you see that minus t minus O into 1 minus O into xj. So this is a very rhythmic expression, t minus O into 1 minus O. So hence, the change in the weight Wj is minus alpha into dou Ew by dou Wj. So this minus and minus, they cancel each other. So alpha into the rhythmic expression t minus O into 1 minus O into xj. I have been telling you that this error of classification is always projected onto the feature value, and then the resulting value would be the change in the weight. So never forget the participation of the feature vector while correcting. Error projected onto the input feature vector together will result in the change of amount of weight. So this is how it is done. Of course, you can write the vector version of this. W1 or W1, Wj, Wd, if you put all of them together here, it will be W bar is equal to, if you put all of them here, it becomes W bar plus, so we have written this. Alpha is common for everything. T minus O alpha into T minus O. T is because each sample is input, because this is stochastic gradient descent. So for every input sample, there will be a scalar T value and there will be a scalar O value. This is a scalar, this is a scalar, this is a scalar. O into 1 minus O. This is a scalar multiplied by take x bar. So this is the, instead of talking about each and every weight, you see that by vectorization, you can calculate the new weight vector. The new weight vector is old weight vector plus a scalar value. The scalar value is alpha into t minus O into 1 minus O multiplied by the vector. The vector is x itself, the feature vector itself. So this is how you can apply the gradient descent and reach the final set of weights. So maybe I would like to demonstrate the working of this algorithm. We'll go to our co-lab. Yesterday we have implemented the Perceptron. Now we would like to modify, because now we have a new learning algorithm where weights are modified as the weight vector, new weight vector is old weight vector plus a scalar alpha into t minus o into 1 minus o multiplied by the feature vector. So I will save this because most of the code is going to be the same pre-processing code. So I'll make a copy, and this copy of Perceptron, I'll change it to Sigmoid. Sigmoid.ip. So let's go ahead. Import NumPy as NP, pandas as PD, matlab.pyplot as PLT, and import IO. Yeah. Okay, we have imported all the required packages. Now, once again, we are taking the iris classification. So I want to read the data so that the data is pre-processed and arranged as X and Y, the target class, and the feature vector. So let me choose the file. I have iris file. Yeah, there is a question in the chat. If learning rate is small value like 0.001, then it will take more time to reach global minimum and consume more resources. You are absolutely right. That's what I have been telling you. My experience has taught me that in science, in technology, in real day life, in our personal life, in our professional life, one needs to be moderate always, modest and moderate. In fact, I am amused when I look at philosophically the two questions that were raised regarding learning rate and the threshold of classification. So, as you rightly said, dear user 217, I respect your question. Yes, definitely true. I should not be very overcautious thinking that pessimistically I will lose the minima, so let me make it as small as possible. No, we do not do that. And as I already said, we should not hasten and make it as maybe 0.3, 0.5 or zero point 0.6 or 0.8 or ignore altogether. Yes, we should never stand at the two ends of the spectrum of possibilities. Instead, we have to locate ourselves somewhere in the middle of the spectrum, whatever may be the spectrum. It could be a learning rate or it could be any other aspect of human life. So, as you rightly said, it will take more time. So, maybe around 0.1 is mostly suggested value, 0.1, 0.2. And when you start running your programs on your own, you will soon realize, you yourself will be convinced. Nobody need to tell you. You soon will be convinced that yes, 0.1, 0.05, 0.08 is likely to be the correct learning rate.
It's
Did
user
you get?
27.
Yes,
User
Ramakrishna.
20. Eh, It is user 27, sir.
Yeah, it's user 27. Did you get the answer or do you have any following question? Very good, nice. So we have imported the packages and we have uploaded our iris file. And yesterday I have shown you how does our iris file look like and what did we read. So you can look at uploaded of iris.csv. It is a dictionary. Basically, it is a dictionary. So this is what we have read. It consists of multiple lines. The first line is the header line. Yeah, then there is a carriage return and new line character. Then you have 1, 2, 3, 4, 5, 6 values. The sixth one is a string value which says the class of the flower, Iris setosa. Then carriage return new line. Then you have once again 6 values. Okay. And now what we do is to make it more amenable for our processing, we make use of pandas. And from this dictionary, we take the lines of data so that in the data frame, there will be individual records row by row. So I read the data and then I sampled it. I told you, in my initial days of learning machine learning, I made a biggest mistake and then could not come out of it at least for a week because I never realized what was the problem and nobody told me. The problem was I have written right code. In fact, it's not my code. I have borrowed that code from somewhere. And then I tried to execute that code with this iris data. But unfortunately, the iris data consists of 50 setosa, 50 versicolor, and 50 virginica structurally placed in the file. So I have been training with this organization of the input. So my model is never learning and not even an iota of my program is at mistake. It is completely correct. And later on, I realized that this model is unable to learn because I am forcing it to learn looking at 50 uniform samples, followed by another 50 uniform samples, followed by another 50 uniform samples. How can we expect? In fact, we cannot expect a human being itself to learn from showing large uniform data in chunks because we will be carried away by the previous chunk of large uniform data what we have seen, the latest, whichever is there on top of the stack. So we'll be carried away. So the model also was getting biased. So then I realized that you need to shuffle, you need to randomize your data so that the samples are input to the model in a random order rather than all setosas followed by all versicolor followed by all virginicas. It was a very nice experience and frustrating experience for me for a week. So you are sampling it and you want to take all of them back. So fraction equal to 1. If you say fraction equal to 0.8, only you take 80% of the values. And then I told you I am only considering iris setosa and iris versicolor. So a filtered data set. Now, if you want, you can look at data -1, data underscore 1. Yes. So you will see the setosas and versicolors only, and that too in a randomized fashion because they have been sampled. And now I told you yesterday we are looking at a binary classifier, but it doesn't mean that binary classifier should have only 2 features. It's mistaken. Binary classifier, most of the students keep asking me, sir, you say binary classifier, you have taken more features. Binary classifier forces you to take 2 classes, not 2 features. You can have any number of features, 4, 50, 70, 80 features, any number of features. In fact, in our UCI websites, we see that we have a lot of data sets which are having 2 classes, binary data, but the feature vector is very large. 10, 12, 14, 16 features are there. So the feature vector can be of any size, but I considered 2 features only because I'll be able to plot the samples. I'll be able to plot the samples as points. The flowers can be plotted as points based on their petal length and sepal length or any other combination. So that's the reason here yesterday we have taken this is 0 is ID, 1 is sepal length, 2 is sepal width, 3 is petal length. So we have taken sepal length and petal length 1, 3, all the rows. These are row indices and these are column indices. And then I have inserted a dummy 1 feature. I told you for accommodating bias, we have created a spurious feature 1 so that it will get multiplied with the bias W naught and then get added to the network sum. And essentially you are adding the bias because you are multiplying bias with 1. And then these are the labels. The labels are in the form of string, but the strings will not work. You have to encode them, and I have to encode them as 1 and -1 in the case of perceptron. But in the case of sigmoid unit, I have to encode them as 1 and 0 and 1. So yes, and then let me plot. Yes, the plot is correct. Now alpha is 0.1. Maybe if for perceptron you need to start at a very small learning rate, but I think you can go with a weight or with a learning rate of 0.1, and the weight vector is 0.1, 0.2, 0.3. I wanted to show some random assumption deliberately. So that's the reason why I took it as 0.1, 0.2, 0.3. Now, as usual, you want to apply this time the perceptron, not the perceptron rule, but the sigmoid rule. So we know that the sigmoid rule needs a function. So let me include that function. Define sigmoid of x as 1 over 1 plus np dot exp of minus x. So this is the sigmoid function because we need it in case of sigmoid function. So now these are multiple epochs, and this is one epoch where all the samples are submitted if you want to have multiple epochs. So what I'll do is I will comment this and we will see only one epoch. So I think I can as well tab it here, no problem. So for I in range length of x, I'm taking each sample and then I'm calculating the output. So can anybody tell me how the output is to be calculated in case of sigmoid unit? This is perceptron. The network sum, if it is greater than or equal to 0, then the class is 1, else -1. So can anybody tell me how is the output calculated as? Did anybody type in the chat box? You can type in the chat box as well. How is the output calculated in case of okay, the output is sigmoid. Just now I have defined the function. And for this, you need to send the network sum. How do you calculate the network sum? The network sum is weight vector multiplied by feature vector, W naught x naught plus W1 x1 plus W2 x2. So where is our weight available? Yes, the weight vector is already there. We have assumed. Multiplied by, you have the input as x of I, the input sample, ith sample, first time first sample, second time second sample. But this only gives me the vector product. I have to sum up the resulting vector product. So I have to put NP of sum. Yes, I have calculated the value of O. I calculated the network sum of weight vector and the feature vector. And then I have applied the sigmoid function. I got O. And the target label is Y of I because I have already pre-processed X and Y. Now, what is the rule for updating as per the sigmoid? Sigmoid unit stochastic disk. Here the individual weight version is given. I told you when you do programming, you don't go for a for loop and individual weight updation. In fact, the vectorization is used and all the weights are. So this is the form. Alpha into t minus o into o into 1 minus o into x. So alpha into t minus o into o into 1 minus o multiplied by the weight vector, the feature vector. Feature vector currently is the ith sample what we are talking about. So x of I is the sample. So 1 minus o, you're right. I mistyped as 0. So alpha into t minus o into 1 minus o into x of I. So let me run this. There is an error, indentation error. Okay. So let me shift this back and then run this. Yes, I got the weight vector. Just let me give you a feel of what is the weight vector we got. So these are the weights we got. Minus 0.08. See where I have started. 0.1 is modified as minus 0.08. 0.2 and that is modified as minus 0.44. 0.3 is modified as 0.83. Okay, now the final proof lies in getting the correct line of classification. Yes, we got in the first shot itself the correct classification boundary by just submitting our samples only one time. We applied stochastic gradient descent and that to one epo only. Because in stochastic gradient descent, you can have multiple epochs. And in batch gradient descent also, you can have multiple epochs. The number of epochs is not related to the nature of the algorithm. Stochastic or batch will only tell you whether you are changing the weight once after submitting all the samples or you are changing the weights for each and every sample. Here you see that in the for loop, you are iterating through the samples one after another and we are updating the weight. Any questions? And you should remember the previous line what we got in perceptron learning algorithm and this algorithm was different. See, this is the line what we got in the perceptron learning algorithm. Will you see there is a change in the orientation. But still, it correctly classifies. Any questions? Okay. Now I'll move on. Yes, yes.
Can you explain once again y is equal to d of k key for key in y?
Okay, okay, okay. I believe I have explained yesterday, but by any chance if I have missed it.
Yeah, you explained, sir.
Okay, once again I'll explain.
Yeah.
For explaining this, maybe I have to once again go back and start from here. Okay, so that I can show you the transformation of values after each and every step. So we have read the data here. We have the samples filtered. And then what I do is I will divide this code into multiple fragments. Okay, now let me execute this. So I got X. Let me show you how is X. Okay, we have inserted one. This is X0, this is X1, this is X2. Is that clear?
Yes, sir.
Yeah. Now I am showing you y. So what is y? Y is our class, species, classes. So our classes are iris setosa, iris versicolor. But when you are submitting the data to the model, the class cannot be in the form of a string.
Sir.
The class has to be encoded as -1 or 1 or 0 or 1. In the real world, you may have different names for classes. Spam, ham, benign, cancerous, okay, fraudulent, non-fraudulent. You have words normally in the when the real data is given to you in the form of an Excel sheet or in the form of a database or in any other form it is given to you. You have maybe descriptive names for the classes, but ultimately when you work with models, they should be encoded as numeric values. So now I was successful in getting all my class names, but my job is Setosa should be replaced by 0 and iris versicolor should be replaced by 1 and this should be replaced by 1, this should be replaced by 0. So for this what I have done was I have defined a dictionary. Once again I am spreading it into multiple fragments. Okay, I have defined a dictionary. So let me see the dictionary. Let me add one more cell. So I got a dictionary, iris setosa of 0 and iris versicolor as 1. Why did I define this dictionary? Because I want to map iris setosa to 0, iris versicolor as 1. In fact, dictionary is a map. It's called as map in many other programming languages. Or if you look at the whole spectrum of programming languages, the word map, dictionary, these are all interchangeable. So because now I want to map, probably I have taken the help of this dictionary. So what I am trying to do here is, what is D? D is a dictionary. Now what are
Yeah.
the keys in this dictionary? Let me see. What are keys? The keys are D dot keys. I want to see the values. D dot keys. I got the keys, iris setosa and iris versicolor. What are the values? Zero and one. So now what I am doing is, I am using a for loop to iterate through y. What is y? Y is the class vector. And what does the class vector consist of? Strings. So I am taking each string in y. If it is confusing, you can always say d of s. For s in y means for each s in y, calculate d of s. So let us see what does y consists of when you are iterating. First, what will you get? Iris setosa. So this s is iris setosa. D of iris setosa. D of iris setosa is 0. Next you will get versicolor. D of versicolor is 1. So you see that you map, you take each value in y, and because the values of y are made as keys, these keys will be replaced by the dictionary of key value. So you can, this is a normal technique used in Python if you want to map one set of values to another set of values. Of course, there are other ways of doing it also, but I chose this to make it simple. Is this clear?
Yeah. Thank you, sir.
Okay. So that's where the sigmoid unit. But still, I told you, the sigmoid unit is good in giving you probabilities to make better judgment, but still the drawback of not being able to classify non-linearly separable samples. So for that reason, we will go to a neural network where multiple sigmoid units are organized as based on human brain connectionist model. So you see that you have a neural network in this form. So the complexity grows further. You have two features here, x1, x2. If you have more features, you will have more neurons. These neurons are only input neurons. They do not apply any functions. They take x1 and give out x1. They take x2 and give out x2. So now you have another layer where three sigmoid units are placed, and you have the output layer where you have binary classification once again. So you say setosa is 1, versicolor is 0. Of course, iris setosa and iris versicolor problem is linearly separable, so you can still manage with one sigmoid, but we have taken an example here. So you take any non-linearly separable data set, it should work. So in these artificial neural networks, you see that every neuron is connected to every other neuron in the subsequent layer, in the next layer. And there is a mandatory input layer and a mandatory output layer. So this is a mandatory input layer. This is a mandatory output layer, and this is called a hidden layer because it is in between. And you see that every layer in every neuron in a particular layer is connected to every neuron in the other layer. So suppose you have two input layers, two input neurons, and three hidden layer neurons. How many weights will exist between these two layers? Two input neurons and three hidden neurons in the hidden layer. You will have 6 weights. Similarly, here you will have 3 into 1, 3 weights, total of 9 weights. As you increase the number of hidden layers, the number of parameters also explode. And once again, how does this model learn? The same old gradient descent rule what we have applied to sigmoid units, but now you have to derive it for the case of multi-layer sigmoid units. So once you learn the weights by applying the algorithm, what you try to do is you input the sample, and then this is where how the new artificial neural network works. Suppose there are connections to one neuron from inputs. So the neuron, every neuron computes the network sum. As said earlier. So weight into the feature value, weight into the feature value, weight into the feature value, and there is a bias associated, plus bias. So you get the network sum. and then you apply the activation function. There are several activation functions possible. So you get the output. So it need not be 1 or 0 as shown in the diagram. This is applicable to the whole network. So you see that this will calculate H1, this will calculate H2, this will calculate H3. How are H1, H2, H3 calculated? H1 is output by this neuron. How is it output? Let us see. You have one edge coming from X1. So X1 into W11 superscript 1. Why I call it as superscript 1? Superscript 1 represent the weights between the input layer and the hidden layer. Superscript 2 represents the weights between the hidden layer and the output layer, because it's all weights everywhere, weights. So you should be able to differentiate them. That is the reason we use the superscript to talk about the orientation of these weights. Which weight are you talking about? So X1 into W11. There is another edge emanating from X2, and the weight of the edge is W211. So X1 W11, X2 W21 plus B1, you get the network sum. And to this you apply the sigmoid function, you get H1. So you see that you have H1 is equal to your sigmoid function 1 by 1 plus e power minus x of X1 multiplied by W11 superscript 1 plus X2 W12 plus B1. Similarly, you get H2, you get H3. And once you get H1, H2, H3, once again, these as the inputs and these as the weights, this neuron will calculate. There could be more neurons once again here. It's not necessary that there should be only one output neuron. There could be multiple output neurons. So how does this neuron calculate? H1 into W11 plus H2 into W21 plus H3 into W31 plus B1 of 2. This is B1 of 1. This is B1 of 2. Plus, and to this network sum, you apply the sigmoid function. So you get the output. So if there is another layer consisting of multiple neurons, and here is the output layer, what I get here is H12, H22, H23, because there are two hidden layers, and in that case I will name them as H11, H21, H31. So this is how it will be a big network, and this should be capable of doing multi-label classification for samples which are not linearly separable and having very complex decision boundaries. I'll show you one example to know the power of yeah. And then there is a playground of neural networks which is provided by TensorFlow. So this is the playground. Look at the caption, tinker with a neural network right here in your browser. Don't worry, you cannot break it, we promise. That's a very funny and challenging comment from Google Research Group. Tinker with a neural network right here in your browser. Don't worry, you cannot break it, we promise. So here, if you see, you have different kinds of data sets with complex decision boundaries. See this data. There are two classes. And these samples belong to one class and these samples belong to another class. My God, how should the decision boundary be? The decision boundary should be circular. You should be able to identify a circular boundary so that the samples which fall inside that circular boundary with these values of x and y. Yeah. So look at these samples. So you should have a decision boundary like this. Four parabolas. Four parabolas. Look at this is a simple one. I think a linear boundary. These are linearly separable, whereas these are not linearly separable. There is no way you can draw a line and classify the samples. These are not linearly separable. Look at this data, spiral data. So now the challenge is, let me take this most simple. Design your neural network. So there are how many features? Two features, fixed. If you want, you can increment the features, add x1 square, x2 square also. Then if you say plus, more and more neurons, hidden layers will add. If you say minus, hidden layers are decreased. So I am taking only one hidden layer because it is linearly separable. I don't think I need a powerful neural network. So let me reduce. I'm not sure will I be able to classify with one neuron itself. Maybe somebody should tell me whether I will be able to classify with one neuron. So this is my input layer. This is my hidden layer. This is output layer. Of course, my output layer is not shown in the form of a block here. The diagram itself is shown. To make it more illustrative, instead of showing values of 0 and 1 in the output layer, the designers have very smartly shown the data set itself, and they will draw the boundary also, so that will act as your output neuron. So this diagram should be taken as output neuron. They are very smart in making the classification boundary being shown in the diagram itself as the output neuron. So, and there are many other hyperparameters also here. Problem type is classification, regularization rate is 0, regularization type of regularization, L1 regularization or L2 regularization, and what is the activation function you want to use, sigmoid or tanh or ReLU or linear. Maybe I'll take it as sigmoid function. And the learning rate, you can play with the different amounts of learning rate. So 0.1. So now if I click on this play button, the gradient descent rule will start applying, and then slowly you will see how your decision boundary is being learnt. So let me click on this. I think I can stop. In fact, let me reset and be smart enough to quickly stop it as soon as the decision boundary is found. See, the decision boundary is already found. In fact, even if I run it for more time, I don't think there will be any improvement because the correct decision boundary has been found out. This is how the error has decreased. It sharply fallen down and it became the zero error classification. This is here you see total loss and training loss. Okay, no point. I'll stop it. Now let me take this data set and try the same model. Wow. Now it says that all these are yellow samples and all these are blue samples. It has drawn a boundary like this, but it is not correct. Blue samples are on this side, but unfortunately, the yellow samples are also on this side. So it cannot be correct decision boundary. How to find out the correct decision boundary? Let me stop this. Shall I increase more number of neurons? I can increase neurons here. Okay, let us try. Ouch, we got it. These are all the blue samples. These are all the yellow samples. See the decision boundary. How complex is the decision boundary? It learned a triangular decision boundary. Let me reduce the number of neurons and no, it could not. If I increase the number of neurons to 3, probably, yes, it is able to converge and then it is able to do it. It's so nice. Now let me see another data set. This data set, let us try with three neurons. It almost classified them as correctly. So see how slowly it is changing itself. Yeah, let me stop here. See how well it has classified all the blues. See the decision boundary here. This is a decision boundary line. This is a line and this is the remaining. So all yellow and blue are classified correctly. Let me increase one more neuron. 4 neurons, and does 4 neurons help me in any way? See here the number of EPOs. I think it's almost same. Let me increase one more neuron. Oh, 5 neurons is giving me a better decision boundary if you observe. A very robust decision boundary. In fact, we knew actually the samples are like that only. So they are perfectly classified. I'll stop this. You have seen this, we have seen this. Let me see this. The most complicated data set where, you know, each blue points, all these blue points are in love with yellow points. They are unable to come out of it. Each is inside the other. So let us try this. It is trying its level best, but unfortunately unable to classify. Maybe let me add x1 square, x2 square, and then try to. Oh my God, oh my God. See, it almost correctly classified. Maybe one more neuron will do. Let me add x1, x2 also. Let me see. I don't think it has version. So let me remove x1, x2. Okay. And add one more layer. Oh, sorry. One more hidden layer with 3 neurons. Let me add x1 square and wow. See, correctly it has classified. Maybe if I add one more neuron here. No, it's bad. This is better. Yeah, see, all these are blues, all these are yellows. So I think that should be a good motivation for you to further continue your exploration into neural networks, into deep neural networks.